Hello, this is Mark Case from Lehigh Carbon Community College Science and Motion program. Today we're going to be taking a look at setting up an experiment to try to measure voltages created in electrochemical cells, sometimes called galvanic cells as another name for them. We have a device, a LabQuest, that is set up with looking at some probes to be able to check to see the voltage. So I have a battery here, just a regular AA battery. And when I hook it up by pushing the electrodes from the sensor, I see that I'm getting a negative reading on the screen, negative 1.473. Well, that's because the battery says that the top stem is the positive side and the flat end is the negative side. So if I reverse the polarity or reverse the positions of the black and red wires that go into the sensor, I now get a positive reading of about 1.490. This is a 1.5 volt battery, so that's pretty good. So basically the black lead is the one that's hooked up to the negative. It's the ground. It's where oxidation is going to occur in the reaction, where something is losing electrons and flowing into that lead, and the red one is for your positive. What we're going to create is individual half cells, and you will see that they are identified on the filter paper as M1, M2, M3, M4, M5. These are 5 different metals with their solutions that are 1 molar concentration that are there. In the center, we have to have what's called a salt bridge. And that's going to be something that's not going to react with the chemicals that are in the half cells, but it's going to provide a flow of negative and positive charges from the potassium, and in this case, the nitrate ion. So I'm putting that on first because, as you can see, it's starting to spread out. At each half cell position, so for metal 1, for example, I'm putting a couple drops there. For metal 2, each one gets a few drops. It's going to run into the drops that came from the potassium nitrate, and now it completes a circuit. It allows them to have a continuous flow of charge between the one half cell to the other half cell. So I'm adding some to each space. Some of them I have in pipettes, some of them I have in the bottles. And finally, I add the 5th one onto it. You'll notice that metal 1 and metal 5 have a color to them, which might be a clue as to their identity. I'm going to place metal 1 on top of the solution that has metal 1 ions in it, and I'm going to place metal 2 on top of the solution that has metal 2, etc. So metal 3 with the solution 3, metal 4 with solution 4, and then metal 5 with solution 5. Now, what we would like to do is to measure the amount of voltage between these 2 half cells. So I'm taking my leads that I was using. The electrochemical cell is going to be completed by pushing down against the 2 different half cell values. And you can see between metal 1 and metal 2, when I push down, I'm getting a voltage of about 8.77, 8.78. The voltage will start to drop over time as you start to have a reaction beginning to occur. So you should try to get your reading, initially, and get what's the highest value that you get. Okay. If I would have reversed those, I had the black wire on metal 2, and I'm switching them around. Notice that I get about the same reading, but now it's a negative quantity. So negative 0.85, and it's dropping. So I want to go through and test each one of these. So I have metal 1. I'm going to put the positive back on there with metal 3. And you would record this value so that you can compare that. That's giving me a reading of about 0.462. Metal 1 with metal 4. Now notice this is giving me a negative 0.461. So I should switch the position of the black and the red wires. So if I reverse those, I get about the same reading, 0.471, but now it's a positive value. So that means that the black wire, which is where you have electrons flowing into it, metal 1 is being oxidized and losing electrons, and metal 4 has to be gaining those electrons. So again, you see that you just change the sign when you switch the polarity of which one has the black wire going into our meter versus the red wire. I want to continue. I want to take a look at metal 5 with metal 1. So that gives me a value of about 0.518 was the highest that I hit for that value. And the only one that I switched the position of the red and the black wire was between metal 1 and metal 4. I would then want to go and do continuum testing. So let's take a look at metal 2. I don't have to do it with metal 1. I already tested that one. So metal 2 and metal 3. Again, that's a negative. So let me switch the positions. Try not to block your view here totally of what I'm doing. But that gives me between metal 2 and metal 3 a value of 0.392. Looks like the highest. Try it again. .392 is the highest reading there. Metal 2 and metal 4, I'm getting a 1.32. Metal 2 and metal 5, you don't have to worry about writing these down. I'll give you a table that have the values in. So that's giving me a quantity of about 0.318 was the highest I think I saw on that one. And let's try metal 3 with metal 4. That gives me a reading of 0.931. And the black wire is on metal 3, so that one's being oxidized. Metal 3 and metal 5, that's a negative sign. So once more, I have to switch the wires and put the positive on metal 3 and the negative, and that's giving me only a 0.073 value, a very small value of voltage. 0.074 is a higher value. Finally, I want to do metal 4 and metal 5, with metal 4 being the positive and metal 5 being the negative. I'm getting almost a volt. Oh, there's a volt, 1 volt as a reading. So you now can compare and take a look at this data and decide what's the potential of them to lose electrons and undergo oxidation, or what's the potential of them to gain electrons and undergo reduction during the course of creating a voltage flowing between the two of those. In the AP test, they will always provide you with a listing of the reduction potentials that you could then predict what would be the amount of voltage that you should get by putting together two of the combinations that we were looking at for these individual metals. Since we don't know the exact identity of each of these metals, what we're going to do instead is decide which one is normally undergoing oxidation. So that's the one that will be hooked to the black wire the most frequently. And which one is usually going through reduction, which will usually be hooked to the positive wire. The one that normally is hooked to the positive, the red terminal of our voltmeter that we're using, is going to be the one that has a higher reduction potential, they call it. And if you just reverse the equation, instead of having them gain electrons, if you have the situation with the metal losing electrons in the oxidation, it will be the same value, but it will only be opposite sign, negative versus positive, as you go through that. So you are to try to rank order these metals in terms of looking at the one that's going through the reduction as the lowest potential to the highest reduction potential, and then predict the potentials of all the combinations of your cells that you would get. To actually look at data and to be able to compare that, on the AP test, they used to give you a chart that would show you all of these individual values. Let me go down here and show you the chart that was the standard that would be on all AP exams to have you be able to figure out what voltages there are. But you'll see that up at the top, the one that is most likely to undergo reduction is fluorine, which makes sense because that's the most reactive non-metallic element on our periodic table, and that gains electrons most readily. So it has a potential voltage of 2.87 just for that half reaction. But if you're going to have that gain electrons, then you always need to have something else losing an equivalent amount of electrons. So as we scroll down and we see, where are the metals that we were studying, we were looking at copper, for example. We knew that was a blue solution. So that might be giving it away that that's what we were working with. There's actually 3 equations that are shown here for reduction potentials. Copper has a +1 charge gaining a single electron. Copper has a +2 charge where it normally exists as gaining 2 electrons to go to copper metal. And then there's also the possibility of copper 2 just gaining a single electron to go to copper 1. The one that we're normally focusing in on is a complete reaction. So the copper 2+ would go down completely to copper metal, and that would have a 0.34 potential for that to occur. If I would mix together a reaction cell that would put together the copper and look at that as a 0.34 and compare that to the fluorine, which we will never do, because that would be a poisonous gas and we're not going to work with that in this class. But if we put the two together, what we would do is basically just look at the copper reaction and reverse it, since it has a lower reduction potential as 0.34, reverse that and change the sign and make that a negative 0.34 value, and then add that to the 2.87 that we have from the fluorine. That would give you the predicted voltage of the whole cell overall. If we compare that to maybe one that we did react, we said that there was some iron that was in there. The particular iron that we were using was iron 2. So as I scroll down, I can see that there's copper as a 2+, gaining 2 electrons to copper metal as a 0.34. The iron as a 2+, gaining 2 electrons to iron metal is a negative 0.34. So always think positive when you're trying to decide which one's going to be reduced. Whichever has the higher reduction potential, that's the one that stays positive. So copper stays as 0.34. Reverse the equation for the iron, and the iron metal now loses 2 electrons to iron 2+, and change the sign to a positive 0.44. So the predicted voltage would be the sum of positive 0.34, positive 0.44, and that gives you a positive 0.78 volts. We can go back and check and see what number we came up with actually in the lab and go from there and see how that would combine. Just for sake of argument, if we had used iron 3, and it might go through a reduction down to iron 2 with only 1 electron involved in that process, that would still be a higher positive value, 0.77. So in that case, that means that the iron would go through a reduction, and then the copper would be oxidized. We would reverse the copper equation and have it a negative 0.34, and we would add that to the 0.77. In reality, we have to double the iron equation from iron 3 plus 1 electron to iron 2, so that we end up having a total of 2 electrons that are going to be gained, and then the copper would have 2 electrons lost. But we don't change the value of the reduction or the oxidation potential, because it's like density, where it's an intensive property. It doesn't matter how much of the material you're working with, you always have the same quantity. So you don't double the 0.77, even though you need to have twice as many moles of iron 3 reacting as you have to have in terms of the moles of copper reacting with that.